All right, so let's finish up that carbonyl chemistry that we were talking about when it comes to different nucleophiles. I think where we left off last time was we had gotten through oxygen nucleophiles, we had gotten through nitrogen nucleophiles, and then we even took a little bit of a view of how do we use water to do the reverse reaction in order to do hydrolysis and specifically we talked about hydrolysis of acetals. So what I want to do is I want to go ahead and start with the sharing and the caring, and not the carin, but I want to move on with where we left off then. And so this is where we were. We did the mechanism for the hydrolysis of acetals. And so we said, look, it's always an equilibrium. If we have to remove water to form the acetal, then we can add water and with acidic catalyst to do hydrolysis of the acetal. Now, we can do the same thing with imines and enamines. The reactions are the same. So H plus with water, H plus with water does the hydrolysis reaction, reforms the carbonyl. And I would almost say, here's some reactions that I a little bit hesitate to put them on officially on the reaction board, although you do kind of have to know them. But we did this reaction already where I did it in the reverse direction with minus water. So I want to put it on the reaction board in the sense that, you should know that this is the reverse of the other reaction that we did. This is hydrolysis of an imine. This is hydrolysis of an amine. This one was hydrolysis of an acetal. All right, so all of these reactions involve mechanisms from their formation that go in reverse. So we talked specifically about the formation of, how did I do that? How did I make it white? I did something quick. I want to figure that out so I can quickly change colors. Anyway, here's the form. This is what we talked about when it came to the mnemonic for the formation of an acetal. Then we specifically talked about, well, how would we do this mechanism in reverse to do the hydrolysis of an acetal? We said, well, we would go backwards, and remembering that the opposite of a nucleophilic attack is a loss of a leaving group, the same way the opposite of loss of a leaving group is a nucleophilic attack. And that way we would know the 7 mechanistic steps that represent the hydrolysis of an acetal. All of the other things are approached. So 1 and 2 are approached the same way. You have to reverse the mechanism. But we just have to remember that we're doing the steps in a reverse order, and at the same time, the opposite of a nucleophilic attack is a loss of a leaving group, and the opposite of the loss of a leaving group is a nucleophilic attack. And so this is one of those things that I was talking about. The reactions and mechanisms that represent the hydrolysis of imine and hydrolysis of enamine are analogous to the hydrolysis of the acetal, but they're not exactly the same. So if there were going to be an assessment in the future, 1 and 2 in the near future, 1 and 2 would not be on that assessment. And so I do, though, want you to think about these mechanisms for imine and enamine and think about how you would apply hydrolysis to make them go back to the carbonyl groups. I'm not going to show those mechanisms because at this point, I think there is some expectation that you could apply those mechanisms in reverse. I did show you how to do hydrolysis of an acetal, and so we'll go from that point forward. So let's move on and talk about sulfur nucleophiles. Remember that sulfur is group 16. And what else is group 16? Oxygen is group 16 as well. So for the next couple of reactions, what I'm talking about are going to be not just analogous to their chemistry for oxygen, they're going to be exactly the same, where all you're doing is you're replacing the oxygen with a sulfur. So everything else is exactly the same. You're literally just replacing the oxygen atom with a sulfur atom. And so that means that we can take a carbonyl group and we can react it in H+ catalyst with 2 RSHs, 2 thiols, removing water, and we can form a thioacetal. We could even use a thioacetal like it was a protecting group, because remember, these are equilibriums that are based on whether or not you're adding or removing water. And we can form a cyclic thioacetal. The only thing that's new, that's totally new, would be that you can take a thioacetal and react it with something called Raney nickel. And if you think about it, what does nickel do? What should nickel be? You should be thinking to yourself that nickel would act as a reducing agent. Good job. Good job for those of you that typed in text. Good job. Yeah, it's a reducing agent. And so this is actually what it creates. It creates an alkane. So it completely reduces the acetal or the thioacetal all the way back down to an alkane. So this one is new, but when it comes to these, the reactions and mechanisms, here, let me just stop the embarrassment there. There we go. Are exactly the same as the oxygen analog. All you're doing is you're replacing the oxygen with a sulfur atom. That's it. Everything else is exactly the same. Both the forward and reverse reactions for forming a thioacetal and the hydrolysis of a thioacetal. Exact same steps, exact same mechanistic moves, just different atoms. So any questions about that? Okay. Well, that's it for sulfur nucleophiles. The other nucleophiles that we mentioned were both hydrogen and carbon nucleophiles. Hydrogen nucleophiles are something that you should already be familiar with, both in terms of the reactions and in terms of the mechanisms, because they are essentially just repeats from the alcohol chapter. Lithium aluminum hydride with water in the second step will produce an alcohol. The same thing with sodium borohydride. It's only one step though, sodium borohydride, and methanol will produce the exact same product as above. And you should know these mechanisms as well. If I take a carbonyl group and I'm reacting either sodium hydride or lithium aluminum hydride, in either case, they are hydride delivery agents. And hydride is H minus. And so the hydride attacks the carbonyl carbon in the way that you've seen before. And this is where some proton source comes along. And whether or not that proton source is water, maybe it's methanol, but in either case, we're making our secondary alcohol product. Sorry about the delay. Okay, and so the only thing that I want to make sure to add is this part here. This really is a tetrahedral intermediate. And so remember that carbonyl groups are trigonal planar. And so if I have a trigonal planar carbonyl group and I'm going to add hydride to it, that the hydride can react from above or the hydride can react from below. And depending on which way it reacts from will determine whether or not I get this alcohol or I get this alcohol. But at the end of the day, it's going to be 50-50 racemic mixtures. So keep in mind that when we do these reactions with unsymmetrical ketones, that you're going to have some stereochemistry to sort out. All right, and so that's it for hydrogen nucleophiles. It really is just a review of some reactions that we already know. Carbonyls react with hydride to form alcohols. They get reduced. And so that moves us into carbon nucleophiles. And I want to talk again about one of my favorite carbon nucleophiles. You know it, you love it. It's your favorite negatively charged carbon. It's Grignard. So again, we do know how Grignard reacts. We know the mechanism associated with Grignard. And so I want to remind everybody that if we're dealing with an unsymmetrical alcohol, or excuse me, an unsymmetrical ketone, that you will end up with both versions of the stereoisomers in a 50-50 racemic mixture. Yeah, so when are you going to have to think about stereochemistry? The question was asked, how do I, when am I going to have to think about the stereochemistry? Well, it really is in the starting material. If the starting material is symmetrical, then the resulting alcohol has two groups on it that are identical, and so that it does not form a chiral center. However, if it's unsymmetrical, then it does form, assuming that the R group is not the same as methyl, so R prime and R, you do get two different, you get one, not two, but you get 1, 2, 3, 4 different groups. So this is a chiral center. So you will have to consider that the other product that gets created in equal proportions is the one where you switch the OH with whatever this R group was. Does that make sense? Hope that helps. Good. Good. Okay, so another carbon nucleophile is something that we've been waiting for our entire organic chemistry lives to encounter. So we can take a carbonyl group and we can react it with a cyanide salt and a proton source like hydrogen cyanide or HCl, and we can get it to do a nucleophilic attack and produce a cyanohydrin, a cyanohydrin. The reaction mechanism is not going to be surprising. The CN acts as a nucleophile. You should know this from Orgo 1, where we looked at CN as being something that readily does substitution reactions, but does not do elimination reactions because it acts only as a nucleophile. And then we need our proton source to reprotonate the oxygen and form the product cyanohydrin. The problem with this is that it's deadly, toxic. And so that's why we would probably in a real lab use something like HCl to be the proton source instead of hydrogen cyanide. This is a liquid at room temperature. So you wouldn't want to get any of that on your skin. Now, the reason why we've been waiting for our entire organic chemistry career is that we talked a lot about in substitution way back in Orgo 1 that if we did a substitution reaction with CN, then we can put a CN group on a carbon chain. It was effectively one of the things that changed the carbon-carbon skeletal structure. But one of the things that I talked about in Orgo 1 was, well, at that point in our chemistry career, it's not particularly useful because we didn't know what to do with it at that point. But now we're actually going to learn a reaction where we can do something with it. If we take a cyanohydrin or any cyano group for that matter, and we react it with lithium, aluminum, hydride and water, then we can reduce the CN to an amine. We can reduce the CN to an amine. So now we're finally seeing some useful chemistry with this cyanide anion, with the cyanide group. I can also oxidize it, or not actually oxidize it. I can change its functional group, because if you were to calculate the oxidation number of the carbon in a C triple bond N, you would get the exact same oxidation number as you would for the product of the reaction of that group with acid. So it's not strictly oxidation in the sense that you're changing the oxidation number, but it is oxidation only in the narrow sense that you are adding bonds to oxygen. So it's not necessarily, it is kind of wrong to put it in your brain and say oxidation, because you're not changing the oxidation number. But if you need to memorize it that way because you're adding more bonds to oxygen, then you're not going to make me upset, and you're not going to make anybody else upset, as long as you get the right answer, that you're forming a carboxylic acid from the CN group. So you're removing the nitrogen completely and replacing all three bonds with bonds to oxygen. So those are three new reactions for sure. We really did just figure out what's good about CN, and what we'll do is we'll come back to CN and we'll come back to carboxylic acids in the next chapter. We'll really dig in a little bit deeper into those mechanisms, into those reactions. So for right now, we're going to put that away. The last thing that we want to talk about in this chapter is the stabilized Wittig reaction. There is going to be one other reaction that we talk about, Baeyer-Villiger oxidation, but it'll be just sort of like right at the end. It'll be like one of the last thoughts that we have. But we're going to spend some time with the Wittig reaction. And I hope that you'll see why it's important. Here's the Wittig reaction. So let me give you just the basic reaction. If I take a carbonyl group, so again, this is a carbon nucleophile, and I react it with a Wittig reagent. The double bond stays, but I replace it with a carbon. So the Wittig reagent replaces the oxygen in a carbon-oxygen double bond with a carbon group. And I hope you're seeing why that's important from a synthetic point of view. If I can take a carbonyl group and turn it into a carbon-carbon double bond, not only have I added more carbons to the chain, but now I've got a double bond, which I can do a lot more chemistry with. Remember, we've got all of those reactions from Orgo 1, where we do addition reactions to alkenes. And so I hope that you see why this is an important reaction. Okay, well, let's think about the mechanism here. How does this mechanism work? So this is one of those mechanisms that doesn't fit well with the 3 or the 4 mechanistic moves, because the first step involves something that isn't well described by those 4 moves. It's a 1,2 cyclo addition. What happens is the carbon attacks the carbonyl carbon at the same time as this double bond attacks the phosphorus. This leaves us with a cyclic intermediate, a cyclic tetrahedral intermediate. Remember that phosphorus can have an expanded octet. So I'm going to show 5 bonds to phosphorus, but that's going to be okay. In the same way with the formation of the final product, it involves 2 arrows at the same time. And then it has so not a lot of steps, but definitely sort of like you can't really describe it. It is sort of a nucleophilic attack, but it's a nucleophilic attack from both of the different, it's a nucleophilic attack from this carbon to this carbon, but it's also a nucleophilic attack to the phosphorus. So it's both species are doing the attacking at the same time. It's sort of like elimination in this next step. So it is sort of like loss of a leaving group, but the phosphorus is losing the carbon, that's leaving from the phosphorus, and the carbon is losing the oxygen. The oxygen is leaving from the carbon. And so they don't fit real well with the previous mechanistic moves that we learned, but it is only 2 steps. And the major feature is 4-membered cyclic intermediate, and 2 arrows in each step. All right. Now we got to dig a little bit deeper into the Wittig reaction. The reason that we need to do that is because there are varying stereochemical outcomes. Yes, the question is asked, pH is phenol, right? And the answer is phenyl, not phenol, but it is a phenyl group. So it is a benzene ring attached to the phosphorus. In my sloppy drawing. Okay, how do I make a Wittig reagent? And so it is important for you to know how to make a Wittig reagent. And so let's use methyl bromide as an example of how this is done. A halogen or an alkyl halide is reacted with PPH3 and then followed by butyl lithium, which is 4 carbons that has a negative charge on the end and a counter ion, a lithium counter ion. And this is how we make ultimately the Wittig reagent. The PPH3 has a lone pair of electrons, and this is the important part. It reacts in its first step with the alkyl halide in an SN2 reaction. So this does limit what works as a Wittig reagent. And we'll talk just a little bit more about that in a second. So at the end of this step, I get and this is where the butyl lithium comes in. The negatively charged carbon comes along and pulls off a hydrogen. And that's what gets me my Wittig reagent. And now what I haven't shown about the Wittig reagent is that it's actually resonance stabilized. So the lone pair on the carbon can form a double bond with the phosphorus. And so you often actually see it as this. And so this is the Wittig reagent. Okay, so remember that the first step is an SN2 step. So normal SN2 rules apply. What does that mean? Primary substrates are great. Secondary substrates, not so great. And what about tertiary substrates? They're not going to work at all. So this is important to keep in mind when you're thinking about a Wittig reagent, especially when it comes to synthesis. We are going to be using Wittig reagents to do synthesis problems, certainly in the homework, certainly in your practice, and certainly on assessments. And so when you're thinking about that going forward, remember that that first step, and that's why we show you the reaction mechanism of how to create a Wittig reagent, you have to keep in mind that the first step is an SN2 step. And so all of those normal SN2 rules apply. And specifically what we're thinking about are the substrates, is the substrate. Now, there is some stereoselectivity that's involved. For most basic situations, we'll observe the Z stereoisomer as being the major product. So what we're going to do is we're going to, for most of these Wittig reagents, the Z product will be the major product. The Z stereoisomer will be the major product. This changes, however, and this is why we're talking about it, if attached to the Wittig reagent is an electron withdrawing group. So it ends up being a discussion about stabilized Wittig reagents. Let me give you an example here. What if I had a Wittig reagent like this? Here's my group, and instead of being a CH3 group, what if it is an ester? This is an electron withdrawing group. If this group that's adjacent are attached to the carbon that is part of the Wittig reagent, then you get additional resonance stabilization happening and this additional resonance stabilization leads to a different stereoselectivity. And so what I want to do at this moment is just show the additional resonance structure. Come on, come on, come on. So the first two are the normal resonance structures that we would show for a Wittig reagent. But I've also now got this double bond characteristic here. You're seeing the electrons withdrawn away from the nucleophilic carbon. And this extra resonance structure leads to more stability. And this extra stability results in a different stereoselective outcome. Now, one thing that happens is Klein doesn't say why. And so it's just one of those rare situations where they just don't explain the whys of it. But the ultimate outcome is the following. If there's an electron withdrawing group attached to the Wittig reagent, we don't see Z stereochemistry. We see E stereochemistry. In this case, it's the major product. So the Wittig, I showed you guys the Wittig reaction, and I gave you the little asterisk, and it's still tiny bit, it's tiny, tiny right there. It still said, here's the, actually that's the formation of the, how to form the Wittig reagent. You do need to know that reaction. You need to know the basic idea behind a Wittig reaction, which is you're forming a carbon-carbon double bond, which can then go on to do other chemistry. But there is stereoselectivity involved in the reaction. And that stereoselectivity is complicated by the fact that it changes based on what the Wittig reagent looks like. If it's a Wittig reagent with just carbon chains on it, then you see that Z is the major product. But if there's an electron withdrawing group on the Wittig reagent, then E stereoisomers become the major product. Okay. All right, so that's it for Wittig. You know, there are other electron withdrawing groups. So I gave you an example that was an ester. I can show you an example involving a benzene ring. The short of it is that the electrons can be delocalized, and I'm going to show you this hop that I don't usually show you all the way throughout the benzene ring, and there's lots of different resonance structures that can be shown for that one. So this one is also an electron withdrawing group. There's more, this one had 3 total structures. I think this one ends up with something like 5 total structures. But at the same time, it's an electron withdrawing group in the same way. Okay, so what's going to round up or finish off this chapter is the Baeyer-Villiger oxidation. We do start out with a carbonyl group, so here's the basic reaction. And I react that carbonyl group with peroxy acid. Remember, peroxy acid is RCO3H. And then what do I get with that? Let's call this one R. Let's call this one R. Let's call this one R prime. I get carbonyl group remains in place, but I get an R group that sort of gets an oxygen. I get the R group, an oxygen inserted between the carbonyl carbon and the other R group. And so it turns out to be an ester is the final product of this reaction. There's an interesting mechanism involved with this reaction. And so let's take a look. What I want to do is I want to make sure that I'm keeping track of the different R groups, because which R group stays is the ones that were already on the carbonyl carbon. This oxygen does a nucleophilic attack. And now we end up with an interesting intermediate. There's the two original R groups. There's the new bond to the oxygen. Of course, that's positively charged. It's still it's still a peroxide. And here's the other R group. Proton transfer moves that proton onto the carbonyl carbon. And that forms a positively charged carbonyl carbon. Here's where all the fun takes place. That R group attacks the oxygen. It literally is like a hydride shift. It does take its electrons and shift over and reconnect to this oxygen. These electrons form a double bond here, and these electrons come back up to the oxygen to get rid of that positive charge. And so what do you end up with? You end up with the R group, and then let me just color code it with this oxygen, and you end up with that. All right. So it's another interesting mechanism, and I know that we've learned a lot of mechanisms in the carbonyl carbon chapter, but this does it. I know there's like about 10, 11, or 12 of them or something like that. And so it's going to be important to get some practice with them so that you can sort them out. The good thing is that for the most part, they're very similar. It's really about getting that very first step right. So I want to leave it at there for the day. And we'll come back next time and talk about carboxylic acids.